Okay, so I'd like to talk a little bit about the chain rule. You might call the function of a function rule for ordinary derivatives. You might know that as the chain rule. This is the chain rule for partial derivatives. Consider some density rho of x and t. So let's suppose that this density changes in both time and space. So we can think of some pulse of density moving with time, right? So we can think of a wave, perhaps. Because we can think of x, maybe the center position here, we can think of that as being simply a translation, right? We can think of this wave preserving its shape but moving in space. That means we can write density as a function of time alone, a univariate function. This univariate function must have an ordinary derivative associated with it. That is, we must somehow be able to write down d rho dt, but with total derivatives. However, because rho changes with both space and time, this is not just simply the partial derivative with respect to time. It's the partial derivative of rho with respect to time plus the contribution from the spatial component. So we've got this rate of change of rho with respect to space times by how the space is changing with respect to time. Right, so this we call the chain rule. This becomes very important for solving partial differential equations and applying transforms to things. In first year level maths, you don't really see the true power of the chain rule. It's a bit of a mystery as to why you would want to write things like this. We're just going to show an example here. We're going to look at an example that shows you that it's true. Okay. Our example, let rho just be x times t, and let's suppose that x just moves linearly in time, and it starts from the origin. So if you like, you can think about x following this line here, where the slope is this constant value a. All right. Let's use the chain rule firstly to evaluate d rho dt. Partial d rho dt is x. Partial d rho dx is t. And total derivative, ordinary derivative dx dt is a. Okay, so let's just write these bits down, or just tell you what they are. Okay, now what we've actually found is a bit of a surprising expression. D rho dt as a total derivative, as an ordinary derivative, that cannot depend on x. Right, so we actually have to remove the x dependence from this expression. And we do that by substitution. We know x in terms of t, so we merely substitute. So we find the very simple expression d rho dt equals 2at. We could discover that by substituting x as a function of t and then differentiating normally with respect to t. So rho as a function of t, rather than rho as a function of x and t as we've got here, that's just equal to at squared. You know, substitute this in there, you get this. So very nicely, d rho dt is equal to 2at. All right, so that at least illustrates that this chain rule works, although it doesn't yet illustrate why this thing is so useful. Unfortunately, you don't see why the chain rule is so particularly useful until you start looking at partial differential equations and higher level mathematics.